Okay, so we can start again. Before we start, however, I wanted to discuss a small practicality. So, as I mentioned before, I created a shared folder on Google Doc, which now is on the page for this course. And over there, I have shared also the notes for what I'm covering right now and what I covered in the first lecture. So you can find in real time notes which should be covering both this lecture. And the reason I'm doing this is because I sort of peeked a bit over your shoulder and realized you are taking notes in very different ways. So some of you may wish to use their tablet and use my notes and annotate there instead of just, transcribing everything I write. So as I see that as I see it, different people use different formats for note taking, and this can be helpful in some cases. Okay, very good. So where did we stop? We were discussing the use of spinolicity variables as polarizations for the spinors in my amplitudes, and then there was one important part that I didn't have the time to cover, namely how we can write spinor polarization, vector polarizations with this variable. Okay, so an important result here, which we will resort to, is the fact that vector polarizations are indeed labeled by the helicity. This is part of Wigner's classification. One-particle states are characterized by four momenta and little group representations, which in case of massless states is the helicity. So we are supposed to give two vector polarization, one for the positively polarized vector and one for a negatively polarized. And in order to do so, we will use, let's start with the plus polarization, and we will write this as a function of the momentum for the particular vector, photon or gluon we are considering, and then a reference momentum. And in this particular case, we want to write this in terms of a gamma matrix, and then there is a factor, a normalization, and it looks like this. So similar expression for the negatively polarized, in which we are having minus sign overall, and then an exchange between angle and square spinors here. Okay, so very good. So what is this teaching us, in a sense? So first, you should note the abusive notation I was referring to before. So the fact that I'm putting here a gamma matrix is to be understood as either the sigma or the sigma bar part according to which particular kind of spinors I'm contracting it to. This is a common thing. And then we see that the momentum alone in this formalism was not sufficient for specifying the polarization. Instead, I had to complement this with a reference momentum, which I call Q. And this can be a reference momentum, or if you wish, reference spinors corresponding to that momentum. Okay, we will return on this in a second. So far, I would like to discuss the properties of this object as they have been introduced. So the first obvious property, but very necessary, is that these are physical polarization in the sense that they are transverse with respect to the corresponding momentum, regardless of the sign. Of course, this is such an important result that we may want to check, right? So how do you check this? Well, we have that for, I mean, let's consider for simplicity, we consider the plus polarization. So we have that epsilon plus dotted into k would be equal to what? Well, would be, let's just say, proportional. We just consider a numerator, and we would have qk, great, and then there is kk. But then, due to the either antisymmetry of the square brackets or the fact that it's equal to 0 when taken with the same reference, this would actually give you 0. So this guarantees the fact that you have a transverse, you have picked a transverse polarization. Okay, this is the first property. A second property is behavior under complex conjugation. So you have that you take KQ and you take the complex conjugate of this, and you can see, based on the rules I specified before, that what you're just doing is changing the sign of the helicity label, which is a good property to have. And another property to have is that, so let's call H, sometimes I can also call it lambda, where here we have it that H is equal to plus minus or 1, 2. I mean, say that H goes over the physical polarization. You are considering the Lorentz product with this, with an H prime, and you are getting that this is minus, with a minus sign, Kronecker delta of the two polarizations. This is also something that you can check easily, and this is a nice little exercise. To make sure that you know how to use this at an elementary level. Okay, very good. So at this point, and please stop me if you have questions, as always, at this point there is a big unexplained fact here. The fact that, what does it mean? What is the physical meaning of this choice of reference momentum? And the answer to this is found just by looking a little bit more in detail. So let's consider the change of epsilon, and for simplicity, let me just pick the minus polarization. I don't know why I prefer the minus to the plus. And let's consider the difference between same polarization, but we have we pick a different choice for the reference momentum. So we have, instead of Q, you have a Q prime. Okay, so what is this object? Just by plugging in the definition, and I like this example because it also allows us to start manipulating these variables so that we get a little bit of practice in doing so. And hopefully they look a little bit more normal by the end of today. Okay, so we just, there's a minus, so there's a minus sign over there, and then we do the same with a Q prime. K, of course, is the same. Yeah, I didn't write K explicitly, but we are assuming really that we are taking that with respect to the same K. Square root of 2, and there's a Q prime K here. Okay, so far, not terribly enlightening, but now let's collect and use some identities. So let me just make common denominator here, QK, Q prime K. And let's see what we are getting in this particular case. So we're having Q gamma mu K here, and we multiply this. I want to get rid of the minus sign, so I flip the direction over here, K Q prime. And there's going to be minus. And here, the same combination with having flipped or exchanged Q and Q prime. Okay. So now we remember that this can be written in the following way. So the first term, or remember, we just rewrite it in the following way. So this is equal to Q gamma mu, the same in here, but then see this combination of the angle cat and the square bra. In here, this is the same as K contracted by gamma matrix. And in many situations, whenever it will be clear that this is a momentum as contracted by a gamma matrix, I will avoid putting the bar just for having a shorthand notation. And this is Q prime in here, okay? So same thing in here. We are having that this is Q prime, gamma mu, K, and then there's a Q. This is the same combination that we had before. Okay, but now we rewrite this piece, or the second term. We note the property that actually this is the same as flipping the Q and the Q prime and the order of these two. This is something you can easily verify. So let me just put it in here. So you note, or you can easily verify, and I hope you can appreciate at this point that this easy way of verifying just takes into account you using the epsilon alpha beta to like to turn bras into cats and use consistently the sigmas or the sigma bars which are part of this definition in here. This is going to be equal to Q K bar. So the order is, of course, the opposite, Q prime. But then you recognize that but then, hang on for a second, you recognize there should be a minus sign in this into this definition, I think. Yes, very good. And then this combination becomes Q, the anti-commutator of gamma mu K plus K gamma mu, and then there's going to be that this becomes a Q prime. And again, if everything is correct here, I have the denominator which has not changed from the beginning. So we recognize here that this is something that can be done just by the anti-commutator, by the Clifford algebra relation between gamma matrices, the explicit one and the one contracted with K. And the result for this is that this becomes K mu square root of 2, because there is a 2 in here, and then QQ prime QK Q prime K. You see, haha, this is very clear what this is, and this is a gauge transformation, right? Because the shift so keep in mind that these polarization vectors are meant to contract the amplitude, and the difference between two of such polarization vectors obtained with two different values for Q is exactly something which is proportional to the momentum times a factor that is just a factor, well, formed by the Q's in a sense. But the most important thing is that being proportional to K mu, this is just a gauge transformation. So in other words, what I have learned is that Q, being a reference, I mean, deserving now the name of reference momentum, can be shifted by using a gauge transformation on my polarization vectors. So in other words, I am free to pick Q as the way I have introduced it is suggested. And at this point, I would like also to notice some useful property. That are associated to this, namely the fact that I can just consider the Lorentz product between two polarization vectors, same polarization here, which are different momenta. Of course, these are different particles associated to the same reference, with the same choice of the reference. This gives you a zero. Why is that? Because you also consider the identity I gave you before, the one involving no contraction of two sigma matrices or gamma matrices, and you see that they would end up having been multiplied by zero, expressed as the square or angle bracket between two Q's. So in other words, I can make a choice of Q such that this relation simplifies the form of the amplitude. In a similar way, if I have this a polarization vector, and I use one of the other momenta as the reference momentum, because if I can choose it, then it would be a good strategic and sound choice to choose one of the other momenta of the other particles as Q. And then I take the Lorentz product with the an epsilon with the opposite polarization, and K2 as the momentum, regardless of the choice of the reference for this, also would give me a zero. I can choose different Q's for different particles. And this choice can be used to a good choice can simplify expressions. And I provide an example of this in one line. Questions about this? Sorry, which seconds do you mean here, or? The Q here is not, no, it can be arbitrary. So all I need is to have the momentum of this, but the opposite polarization. So the pairing here is between the polarization of one and the reference for the other, provided that the helicity is inverted. Yeah, flip sign of it is very important. And why is that? There's an identity I wrote before, right? This is, I mean, this is worth repeating, but this is not black magic, right? This is something you can verify in one line, and that line is, again, remember the identity, there's an I, there is a J in here. Sorry, let me just write it in this way. And then same thing, K gamma mu L, here, and this is equal to 2, and then you have IK. So the angle and the angle, of course, go together in the bracket. And then you have LJ. You use this identity. And you get a zero whenever I mean, in this particular case, you get that the K2 and the K2 go either in here or here according to which polarization you picked. Same thing in here. So our chief strategy at this point to simplify simple amplitudes, but still gets you quite a bit of manage, is going to be to make a judicious choice for Qs. Okay. Aside from this, there is an identity. Since we are on the topic of nice exercises, so also this, I should say check. I told you how, but check one or both of these to make sure that you understand it. And another useful identity, which is closely related to this, is, well, closely related to that, yes, related to that, is some sort of completeness relation, which I let you verify, and I will use. So we are considering a sum over the physical polarization with free space-time indices. In which one is the complex conjugate. And in this particular case, we're going to have that this identity can be verified. There is the metric here plus an extra piece which depends on K and Q, where this is divided by K dotted into Q. So this is another useful relation that you can verify just with the tools which I gave you or mentioned. Okay. This is a good moment to stop and ask if you have questions. The next step, otherwise, is simplifying the first 3-point amplitude using these tools. Yes, it's probably hidden around there. Yeah.
So in terms of Q and Q prime are two different momenta, right?
Yeah.
So this kind of Gaussian solution is, I mean, sorry if I say something which is wrong, it's not obviously local in Q and Q prime, right?
No, it's not obviously local in Q and Q prime. Yes, this is true. So in general, I can have a transformation of that form, but yeah, this is not going to be necessarily a local transformation. Which kind of makes sense because by the same observation, right, these polarizations are not necessarily local in Q and K because we have something here in the denominator. So by the same property. Yeah.
If I can, I mean, just to this way, can you parameterize the kind of generalized gauge transformations that you use to put amplitude in CKU4?
Yes, and well, I mean, certainly some of this transformation will be part of the generalized gauge transformation. I'm not sure how generalized this. I mean, I don't think that this is a complete parameterization of that, and also obviously, I mean, this doesn't change the amplitude, right? Because regardless of what this non-local term, the amplitude itself is not affected by that. So we can discuss generalized gauge transformations in a later, but there's also other more drastic, if you wish, options here, which are linked to zeros, which are not coming from the kinematical part, but they are coming from the Jacobi relations or the color part. And those are, they give you more freedom, I would say. So I don't think you can parameterize all generalized gauge transformation in this way. But yeah, definitely there is some non-local dependence in there. Okay. Any other question? Well, there are some cases in which you don't want to hit a singularity. Right, and actually there's an example of this coming up very soon. We will see in a second that the kinematics which you encounter at 3 points is singular, right? And so at 3 points, I would really like to put, say this is polarization for particle 1, I would really like Q as particle 2, but I would have obstructions in doing so, because that I'm assuming that to be non-zero. If that becomes 0, then that is a problem. So in other words, here I'm implicitly assuming that you don't have a situation in which these brackets in the denominator can become 0. When do they become 0? When you have a situation in which you have some form of collinearity. I mean that the lambdas, the two corresponding lambda or lambda tilde are proportional to each other. Yeah. Anything? Yes. Just. Mhm. Yes. Yes and no. I mean, so these are like carrying analyticity index or analyticity weight. So it's a completely different space. It's a completely different space in the sense that it's in a sense the space of physical polarizations, as opposed to the range of covariant index. But yeah, and they transform also under different transformation. What is the natural transformation which affects the plus and the minus? Illicit scaling, right? And remember, I was discussing illicit scaling before. So as namely the transformation which changes, say, the angle spinor in a way, and in the opposite with the opposite charge, the square one, and you can see on the face, right, what this is. If I use transformation for Q, there is no change. I have a transformation for K, it has weight, say weight 1, in which comes half from this and half from this, which have the opposite weight, right? So you can see that these two indices obey or different natural transformations rules. And in fact, these polarization vectors, their job in a sense is to go from Lorentz transformation to little group transformation, which is a subset of the Lorentz transformation. I've seen this if you do stuff out of Wigner. Yeah. Yes, absolutely. Everything is contracted here. So there is no free index in alpha dot. Very good. And this is a general situation in the sense that implicitly, at least, the fact that I organize everything in terms of bracket means that I don't like to display alpha dot indices. So you're not going to see a lot of alpha dots unless I contradict myself in a couple of pages. And the reason for that is that it's more convenient to do calculation in a way in which these indices are suppressed. Very good. Anything else here? Otherwise, we proceed to our first amplitude, I would say. And I will keep some of this. Okay, so let's, as an example, you consider one of the simplest amplitudes that we can consider, namely, we are considering at 3 point, of course, 3 level. Yang-Mills amplitude. Okay, so we go from the Feynman rules, and we find a result here, which is which can be quoted out of a textbook, and we label this as a general rule with the eliciting information for our external particles, and this is proportional to gauge coupling constant, and then we write the Feynman rule in the following way. So here we're going to have contraction between epsilon 1 and epsilon 2. Then we have K1 minus K2 dotted into the remaining polarization, plus cyclic permutations, and this is going to be proportional to a structure constant, FABCs. And here, with these cyclic permutations, I take care of using the specification of elicities, right? So that epsilon 3 is always the plus, and epsilon 1 and 2 are always the minus. Okay, so here I can tell you one choice of reference momenta which would not create problems is if we start choosing the one of the other momenta as the reference momentum for one of the particles. So instead, here we're going to choose Q as a reference momentum for all legs. Okay, so that at least we use of the properties listed before, the fact that if you have two equally polarized epsilons dotted into each other and you have the same Q, is going to be equal to 0. Well, this choice already kills one out of the three terms. So what is left in here, just by invoking that choice, is going to be epsilon 2. So ironically, perhaps the one I displaced explicitly is the one which gets killed, and the other two in the cyclic are the one which survive. So this is the form where two momentum conservation has been used to actually give you a factor of 2 and just one of momenta dotted into the other. So here I have a K2 dotted into epsilon 1 minus, and the other piece I write as minus. You can see explicitly this is obtained by flipping the 1 and the 2. And this is again multiplying an FABC structure constant. All right, very good. At this point, I have to put in my presentations for the epsilons, and I end up having a G divided square root of 2, keeping track of the numerical factors, and here I have a Q gamma mu 2. So this is the first. I'm using there for the minus. I'm using the 1 over there. And then for the plus polarization, there is a Q contracted in this way, and there's a 3. So I just wrote this piece. Explicitly, this is Q2. This is Q3. Different brackets. And here there is Q2 to 1 being this, and you can see that the K2 became just the 2 over there, and this is Q1. And here I should have left a little bit more space to write minus the term obtained by exchanging 1 and 2, and this is FABCs. And having written quite a bit, I should ask up there, can you see what I'm writing, or should I be a little bit larger? Yes, that's the question. Sorry, the cube? Yes. So I choose Q as the reference momentum for all 3 epsilons, right? Yes, precisely. Yeah. This F is the structure constant, so we are actually having freely, I mean, if you like, we can actually label, I mean, this is part of the external Okay. I would have to use a slightly different notation to explicitly label. I can say this is A3, and then I could say A is A minus, 2 is AB minus, and 3 is AC plus, if you like. So these are the indices carried by the gluon index, if you like, the adjoint index carried by the gluons for Yamil's theory by the external fields. Yes. And you will say, well, I don't remember Yamil's theory, so what is that F? Well, already from the properties of this amplitude, given the fact that these are bosonic fields, right? So you need to be able, they enjoy a Bose symmetry, which should be manifest in the amplitude. You can see that these objects are antisymmetric, at least. So they are either structure constants or a mystery antisymmetric tensor, which appears in 3-point amplitude of a theory based on a gauge group. So in this particular case, we are considering, there is, so the definition of the structure constant in this particular case, well, we are so here we are assuming a compact gauge group, semi-simple gauge group, and in those particular cases, it should be antisymmetric. Otherwise, you may have problems about which indices you're raising or not, but that's in this particular case. In fact, for this lecture, I would just use SUN as a gauge group. So in that particular case, they are antisymmetric. Then you can build also symmetric, like D tensors, outer representation matrices, if you like, but they will not be the object of this course or lectures. Yes. This Feynman roots, which I quoted. Yes. Open, again, this is one of the accent points from the standard quantum field theory course. Again, we have to get that from somewhere. If you like, you can just write the Yamil's Lagrangian and then expand to cubic order. It's rather simple. Perhaps the overall normalization is something which you want to double check, but you can see right away that this term is coming from covariant, the derivative in which one of these epsilon is coming from, and the other one is just a partial derivative. Okay. Anything else? This is very, very good questions. Now, let's continue here. And hopefully we can finish. So the first, the next step is to use the identity I gave before about this particular combination. So this is going to be equal to G divided by square root of 2. Sorry, this is going to be square root of 2G because there's a factor of 2 coming from using that identity. And this is going to be equal to Q2. So using that identity, essentially produces Q2 and then Q3. And then the Q2 to 1 is already there. And then here we are having Q2 and then Q3 angle brackets. And this is divided by self by Q1. This is minus 1, the term obtained just by exchanging. Okay. So this is the first application of the identity. And then one thing I can do is actually to multiply both numerator and denominator with the angle spinor, in this particular case, 2, 3. So we rewrite this, still fits one line, as, there's an obvious simplification there between the Q2, which I don't need to keep writing. And here there will be a Q2 Q1, which I keep, divided by Q3, Q1, and then here I have 2, 3. And here I'm using a particular identity, namely I have, I can write this term as minus Q3, 3, 2, flipping the order in here. And this is something that I can then simplify using momentum conservation at 3 points. Because this, by momentum conservation, I'm having, this is like K3 slash, and I can express this as minus K1 minus K2. But the latter terms becomes equal to 0 because of, if you like, Dirac equation, or because of the presence of the angle cat2. So these terms can be rewritten as Q1, 1, 2 by momentum conservation. At 3 points. Okay. So having taken this into account, then we can rewrite this. There's a minus sign. If I do everything correct, G, there is a 1, 2 squared. Coming to 1, the minus signs comes from flipping this, and this is coming from that. Q3. And here, now I display explicitly that term. I have a Q2 divided by 2, 3. Of course, you know, this term and this term have simplified. Whereas Q2 is coming from here, so everything is been accounted for. And here there is the term obtained by just replacing 1 with 2 and getting a minus sign. Okay. So at this point, all that remains to be done is to use like a common denominator, and then there is a 1, 2 squared in here, Q3. The common denominator is 2, 3, 1, 3. And then this becomes Q2, 1, 3, minus Q1, 2, 3. Okay. Which I write as plus Q1, 3, 2, just by flipping the spinner. Still with an FABCs. Now I use the last ingredient, is a Schouten identity, which I claimed before is useful. This is, so what is the Schouten identity? That the sum of this term with everything obtained by, say, keeping Q fixed and cyclic permutation of the other indices is equal to 0, which is another way. I mean, after you plug that inside, what you will get Q3, simplifying these terms, and then is 3 to 1, you would get to 1. So the result would be, you have G, 1, 2 to the third power, and then 2, 3, 3, 1, which is a remarkably simple expression, and for reasons that will be clear in a second, I will give the square root of 2 to the color factor, or if you like, to the FABC structure constant. Okay, so this is the simplest expression one can get for an amplitude of class that at higher point we will identify as MHV amplitude or maximally elicited evaluating amplitudes, which involves just, in this particular case, angle brackets. Okay, very good. Yes. No, this is not 0. Well, so at 3 points, special kinematics, either the angle brackets or the square brackets are equal to 0. So there is a special kinematics at 3 points, and keep in mind these are complex momenta, in which this is non-zero, but its cousin is the one in which the elicities are inverted, so plus, plus, minus, or vice versa. So at 3 points, actually, this is literally the next thing I have, but I think this is for after the break. We're going to discuss what happens at the 3-point kinematics and why this is special with respect to 4 points kinematics. Okay. So if you have questions about this, stick around. Otherwise, 10 minutes break, shall we say? And I will meet you in 10 minutes. Okay, I think it is time to start again. So there is hey. Sorry. Okay, very good. So it is time to start again, and I would like to start by remarking something about specifically 3 points kinematics. This is also a question I got over the break. So at 3 points, we have a particular kinematics, because you can see right away that if you take P1 plus P2, this is equal to, well, the Mandelstam-like object, right, 1, 2 to 1. But also this is equal to P3 squared, because just for 3 points, and this needs to be equal to 0. So what does this mean? Well, if you have real momenta right away, you're going to say that these brackets both needs to be vanishing. However, with complex momenta, the situation is quite different, because this relation just means that either the angle bracket or the square bracket of 1 and 2 is equal to 0, but not necessarily the other. So since you can do this with any other pairing of momenta, you can have a 2, 3, 3, 2, or you can have a 1, 3, 3, 1. All of this needs to be equal to 0. You can see that there are actually 2 possible solutions. One of these solutions is that, say, start from the first one. Well, either you know that either the angle bracket or the square bracket needs to be equal to 0. So let's take 1, 2 to be different from 0. Okay, then you write that 1, 2, then multiply by 2, 3. Well, this is equal to, if you like, using momentum conservation again at 3 points, 1, and then there is P1 plus P3. So this is just a re-expression P2 by momentum conservation, and here there is the 3 ket. So this is equal, of course, to 0 due to a combined use of Dirac equations. So this tells you that if 1, 2 is different from 0, then 2, 3 needs to be 2, 3 needs to be equal to 0. We already know from this argument that 1, 2 is equal to 0. By repeating the same argument by multiplying, say, by 3, 1, on the left instead of on the right, you also get that 3, 1 or 1, 3, 3, 1 is equal to 0. And this is one of the possibilities. The other possibility is that the angle brackets are equal to 0, but not the square brackets. So this is quite interesting, and of course, you can see right away, given the properties under complex conjugation of these brackets, which I gave you before, that this is a consequence really of having complex momentum. And this is one of these kinematics, specifically this kinematics is the one which will support the result for the 3-point amplitude I gave you before. You do the very same derivation for an amplitude with 2 plus polarization and 1 minus, and you would land in an expression with just square brackets, which is supported by the other kinematics, namely this one. Okay, very good. So now, I mean, what this does really is that it limits drastically what I can write down at 3 points. So keeping this in mind, we have that, well, generic, I mean, and say that we have an amplitude at 3 points. So now we no longer want to do this with gluons, we can also consider other fields, and let's say that we have field 1 with helicity H1, field 2 with helicity H2, and field 3 with helicity H3. And then we can look for an amplitude expression on this using one of these two kinematics in which each of these brackets, which are the only non-trivial, non-zero brackets at these points, is having a certain power. And we can solve, you know, n1, n2, and n3 in terms of the desired helicity weights. So what this is really like that helicity of internal states, of external states, can be used to bootstrap the amplitude, together with some basic information that you have, for example, the dimension of the amplitude, and in case of the amplitude I wrote down, having an anti-symmetric, I mean, the symmetry of by the exchange of legs or external state with equal polarization. So for example, if I tell me what, let's leave this as an exercise you can do, try to build very simply the amplitude between, say that I have two scalars, complex scalars for simplicity, and then I'm going to have, like, say, a minus or a minus polarization gluons as leg number 3. Try to find an expression for this amplitude and see that it's quite easy to get. And here, if you want to read more about this particular manipulation, I recommend the TASI lecture notes on scattering amplitudes. So let me add this as a reference for in case any of you wants to read more about this topic. Because I see part of my role as a lecturer here is also recommending you some sources in which you can have a pedagogical introduction. Okay, questions about this? Otherwise, I would like to move forward. Yes? Okay, so if you want to have bootstrapping of massive particles, you would need to use a similar formalism, but you would need to have an equivalent formalism for massive particles. And this is, for example, Arkani Ahmed and Yutin Wang have had paper in which this was introduced, and they had explicit formulas for massive amplitudes and at various spins. So the same principle can be used, but there you would need to have, well, if you have massive amplitudes, you would need to have first a spin-helicity formalism which has the little group and not helicity. So you would end up having, in 4 dimension, 3 indices, which are SU2 indices, essentially. And you would have to either soak them up, dress them up, but you would have to take that into account. Aside from that, the principle would be similar in the sense that you would, together with, for example, knowing the dimension of your amplitude, you would just write an expression in terms of spin-helicity brackets and try to fix that, knowing the helicities, or, but not the helicities, the little group or the spin. Yes, both of it. But other than that, it can be done. It just requires a formalism, which I have not the time to illustrate in this. Yes. Well, how would you vary? How would you ask the same questions without? I mean, there is a way of bootstrapping things in which it requires, for example, say gauge invariance. So I would say I want to have an expression with the epsilons, one momentum, because I know what the Lagrangian is, and then I want to impose gauge invariance by replacing each of the epsilon with one with the corresponding momentum, and imposing the amplitude doesn't change, and then you would actually get up to an overall constant. As much as you have here, of course, an overall constant, you will still get your amplitude at 3 points. So probably the answer is that at 3 points, expressions are very simple with spin-helicity variables, but that's not to say that spin-helicity variables are the only way of getting expressions at 3 points. As you increase the multiplicity, you have a very particular class of amplitudes, MHV amplitudes, that are strikingly simple with spin-helicity variables. The bootstrapping philosophy, I would say, is slightly more general than just employing these particular kinds of variables. Okay. Other questions about this? This is very good. And what I would like to do next is on the ways of continuing the example. The next example will be a 4-point amplitude. Still 3 level. And I would like to consider separate diagrams. So again, as before, I will assume knowledge of Feynman diagrammatics, and I will rewrite them in spin-helicity variables by a certain configurations of polarizations, and hopefully land in an expression which is simpler than the ones you will get. And at 4 points, you already see that, I mean, while this expression can be simplified, also keeping covariance, you'll see that ultimately you will end up with an expression which has just, well, just a couple of terms, 2 terms. Okay, so we start, since we follow a particular Feynman diagrammatic here, we start by studying an individual diagrams, and then we obtain the other ones by permutation. So let's look at the S channel exchange diagram in a covariant notation and see how we can rewrite this. So this diagram would give you a contribution which is Ig squared divided by I use, to have consistent notation, S12. I mean, I could just call it S. With an overall minus sign, and then there would be the contraction as in this exchange, epsilon1 dotted into epsilon2, k1 minus k2 with a free index mu, and then you have plus 2, epsilon2 mu, epsilon1 dotted into k2, minus 2, epsilon1 with free index mu, epsilon2 dotted into k1. So all the terms, these are one vertex, and then the other vertex would be similarly obtained by sending 1 and 2 in 3 and 4. So I will represent this explicitly. So you have epsilon 4 mu 3 dot into k4 minus 2 epsilon 3 mu epsilon 4 dot into k3. And here we have, of course, our structure constant, FAB, E, F, C, D, E. So you start having this contraction. Okay, so other diagrams are obtained by permutation. And then you also have a diagram in which there is a contact diagram. So the first step to simplifying this expression, if we understand sort of the formalism that we have, is to make a clever choice for the reference moment, right? So how do we make this clever choice for the reference momenta? Well, there are several choices. The one I would recommend, or the one I would adopt, is we put Q1 is equal to Q2, say one of the momenta on the other side, so it could be a K4. Q3 is equal to Q4. Keep in mind that 1, 2, 3, 4 in this particular case, they have equal polarization. The polarizations there is dictating this choice, and we put a Q1 over here. And now, with this choice, we can write down a list of things which are equal to 0. So epsilon 1 dot into epsilon 2 is equal to 0. Why is that? Same polarization and same reference, right? So this is going to be equal to 0. Then we have epsilon 3 dot into epsilon 4. Same reason that we are having epsilon 1 dotted into K4. Why is that? Because K4 is the reference momentum for the epsilon 1, right? So epsilon 2 dot into K4, same reason. Epsilon 3 dotted into K1, same reason in here. Epsilon 4 dotted into K1, still equal to 0. Same reason, again, K1 is the reference for epsilon 4. And then you have epsilon 1 dotted into epsilon 4. Because they have opposite, as I mentioned before, I wrote that relation, and one of you asked me why are they flipped. So they have opposite polarization, and we have that epsilon 4 is the reference for the epsilon 1. Sorry, that K4 is the reference for epsilon 1. By the same reason, we also have that epsilon 3, epsilon 1, and we also have epsilon 2 and epsilon 4. All these are all 0. You may even wonder if there is an overkill and I set everything to 0, thereby clearly making a mistake. I just note that non-zero, there is this epsilon 2 dotted into epsilon 3. So this is the term I have to keep track of. And I realize that in this particular case, non-zero terms can be associated to the two diagrams, like the diagram I wrote before and the diagram obtained with an exchange. So now this is equal to 4i S12. And then you have epsilon 2. Again, I keep track dot into epsilon 3. I keep track of the polarizations. With an epsilon 1 minus dot into K2. And here we have epsilon 4 plus dot into K3. Okay, and you have also another non-zero diagram, which is represented as, so let me just put labels here, 3, 4. This is 1, and here this is 3, 2, and this is 4. So this is the one obtained by essentially flipping the 1 and 4 or 2 and 3. And this is equal to, again, 4i S13. Same non-zero, this is the only non-zero combination or contraction of two polarizations. And here we have epsilon 1 minus dot into K3. I mean, by exchange in 2 and 3. And there is an epsilon 4 plus dot into K2. And here you have FACE, FE, or BDE to keep the same position of the contracted index. And now I would like to note that these two things are equal to each other. This is not obvious to see. This is a consequence of momentum conservation. So that, say, this K3 can be expressed as minus K1, minus K2, minus K4, together with the choice of momentum for this. Otherwise, I mean, with a different choice of reference momenta, those two terms will not be equal to each other. Okay, very good. And these are the other graphs. The contact graph is 0, and the other graph is also 0. Okay. So now we have dramatically reduced, I would say, the number of terms in the expression. And I would like to continue the simplification. We have effectively 1 or 2 terms, I mean, depending on whether how you account for the difference in the color structure. I mean, the kinematical part is just 1. But then, of course, you have 2 different color contractions, which will follow us mostly along for the ride, except that there's a difference also in the propagators, I mean, the denominator that we will need to consider. Before I move towards this simplification, is there any questions about what I have on the blackboard right now? The key takeaway message here being clever choice of reference momenta. And this being a consequence of the way the polarization have been defined. And I mean, of course, at this point, I hope that everybody believes that I can just do a gauge transformation, and whichever polarization I'm given, I can actually send it into a configuration for which these are the correct reference momenta. Okay. Very good. So then let us continue. So again, I have my A4 here. Yeah. Sorry. So the contact term is 0 because you have 2 epsilons, right? 2 pairs of epsilon which are contracted into each other. And this is the only one which is non-zero is over there, right? So I was going to have another pair of epsilons, and it's equal to 0. Of course, this is a consequence of this very particular choice. And what happens if I use a different choice? I would land in the same result, but it may come from 5 different terms. So the fact that don't expect to be able to start from whichever choice of Q's and land up in the expression I give you, because there's a lot of equivalent expressions which are not the same formally, right? So amplitude, and this is a general property, I would say, have many presentations which are not manifestly the same, but they end up being the same. So everybody, even today, different people in the fields come out with new presentations of amplitudes, which have some very nice properties and very non-trivial property, and they were not known before, even though they are the same amplitudes. What do you mean for choosing a gauge exactly? So you mean using the Lorentz gauge, or? Okay, so wait a second. Yes and no. So this has to do with choosing a gauge. But let's say that I start from the Lagrangian and I want to use the Lorentz gauge, right? The Lorentz gauge is a gauge condition, and all these are obtained in the Lorentz gauge. However, there's a residual gauge symmetry, right, which doesn't change the Lorentz gauge, so that I still have the same gauge condition, but still it's there, and that is the part of the gauge symmetry which is implemented as a shift of the epsilon, right? So all our external states have the same choice of gauge, which is a very standard one. However, there is a residual gauge symmetry, which allows me to move around this reference, and this amounts to picking a reference vector. And I think we have seen a different manifestation of the same in the previous lecture. Also, the fact that you have still a residual gauge transformation. It was said at some point, how do we end up having d minus 2, right? Degrees of freedom. So one of them, you kill them with a choice of gauge, and the other one by having a shift by the residual gauge symmetry, and then you're left with d minus 2, or in my particular case, 2 in here. Okay, does this make sense? So this, in other words, this is not a weird choice of gauge. This is a weird choice of reference momentum. Anything else? Okay, very good. So let's continue, and let's try to simplify this. So I'm having my amplitude here. I don't write explicit polarization, and there's going to be a factor of 4, yes, so there's a 4i. And then I'm going to write the term which is the same as, explicitly putting, and now we need to be very careful about having 4 as the reference for, we're having the 2, 3. Where is it? Over there, the 2, 3. So the contraction of the 2 will be something of this form. Reference 1 for momentum 3, for particle 3, and there is a 1, 3. There, again, I will use the identity over there. I have a number of factors square root of 2, which I should not forget. And then I have the 4, 2, 2, 1 divided by the 4, 1. So this is for epsilon 1, which is up there, yes, and then I have left epsilon 4. So I have 1, which is the reference for the epsilon 4, contract into K3, 4 comes here, and let's see, 1, 4. There's a variety of factors of square root of 2, which they just contribute to getting rid of this 4. And then we use the identity. Well, okay, wait a second. Here we have a multiplication by the structure constant. And this is divided by S12. And then there is a plus F A C E F B D divided by S13. So yes, and then I continue by using the identity, which I described before. So you have that this 4 goes in the 3, and here 1 goes with the 2, goes with colloquially, shall we say. And then I just copy for the ride these two here, these two. 1, 3, 3, 4. The thing being divided by the quantities at the denominator. So we have 1, 3, 4, 1, 1, 4. And then I will not copy the content of these brackets. Okay, so very good. So there is some simplification, some cross simplification already. There is 1, 3, and there is a 4, 2, which gets simplified. And I am left with an expression here, which is 2i 1, 2 squared 3, 4 squared. I have 4, 3, 3, 4, 1, 2, 2, 1. So I have just flipped, gaining no minus sign. And then I have 1, 4, 4, 1, which also could be expressed in terms of a understand variable. And I will express this as an S12, and then the contraction of FA BE FCDE plus the second term around here. So this is already a simple expression, but I would like to derive one in a slightly different way. And in order to do so, I multiply this, as I did with a similar trick on what I did before, by the angle bracket 2, 3, and divide by the same quantity. All right. Very good. So what we can do at this point is by use momentum conservation. So I have, sorry, I'm gone 1, 4, 4, 1, yes. So I'm gonna have minus 2i, flipping one of the brackets, and then I have 1, 2 squared, and then I keep a 3, 4. And then I use 3, 4 to 3, 3, 4 as writing this as momentum conservation and as 2, 1. 2, 3, 3, 4, 1, 4. Sorry, whoops. Why do we use momentum conservation in here? Well, it's just the direct expression of 3, 4, sorry, 2, 3, 3, 4, and then there's a minus sign, and the 3 is expressed as minus 1, minus 2, minus 4. The 1 is the only one that doesn't vanish because of, if you like, the Dirac equation. Okay, so that's the same manipulation as I used before. There's a minus sign coming from that, and then there is 1, 4 for 1 in here, and there is an S1, 2, which I can express. Okay, there is still the 2, 3, which I like to keep, and then I would like to express S1, 2 as S3, 4, same thing, which in turn is 3, 4, 4, 3. Okay, so and this will be FABE, FCDE, plus the other term. Okay, very good. So some simplification are now in order. Okay, so if we manage to keep track of the signs, you have that the 3, 4 and the 4, 3 simplifies with an extra -1. 3, 4 to 3, 3, 4 are there. 1, 4, 4, 1 simplify with an extra -1. So I don't need to keep that into account. And the final result is minus 2i. There is 1, 2, the third power. Keeping this, there's a minus sign. And then there is 2, 3, 3, 4. Let's keep a cyclic ordering, so we flip the sign also this for 1. FABE, FCDE. Okay. Plus a second term. Now, writing this explicitly, actually, I'm going to write minus 2i in this way, and then there would be a minus 2i. The second term, repeating some of the same manipulations which we had done before, you would have still 1, 2. This would be at the fourth power in this particular case, and there would be 1, 3, 3, 2, 2, 4, 4, 1. And here we would have F, A, C, E, F, B, D, E, with our structure constants. And you can see, of course, that these two terms look the same if I express, if I put an extra 1, 2 in the denominator and I increase the power to 4. Okay, very good. So questions about this? This is the result with 2 positive polarizations and 2 negative polarizations. You can do the same game in case you have a different numbers of polarizations, 3 and 1 or all same polarization. If you do that game, however, this works even better in the sense that it becomes 0. So having a judicious choice of reference momenta leads you to actually set to 0 the amplitude in which there's a different helicity configuration with respect to this one. And keep in mind, these are not ordered amplitudes for me. So these amplitudes, I mean, I'll show you how to order amplitudes by next time. But for now, this amplitude, you don't need to care about the order in the sense that everything can be obtained from permutation as long as you are also changing accordingly the color indices. There is a notion of helicity decomposition in the sense that the same amplitude can be can be separated according to the number of, or decomposed. So amplitudes between like fields decomposed according to number of positive, negative helicities. And this is something that will also continue at a higher point. In particular, there is a notion of MHV amplitudes, which is maximal helicity violating. Helicity is not conserved in these interactions. There's no reason why helicity should be conserved. So this violation sounds like there's something wrong with the amplitude, but instead, maximally eliciting violating amplitude will be at any given multiplicity the non-zero amplitudes which have a maximal imbalance, say between plus and minus elicities. And in this particular case, perhaps misleading, the MHV amplitude is also the only non-zero amplitude in this particular case, and there's an even balance between the two. At 3 points, the one with 2 minus and 1 plus, we call that the MHV amplitude, and the conjugate, so to speak, is the anti-MHV amplitude. Okay. Questions about this? So one thing that I should mention is that you may attempt to use the same philosophy which sort of outlined, the bootstrapping philosophy, which outlined for 3-point amplitudes, attempt to do that at 4 points. So what happens if you do that at 4 points? Well, it still works, but it becomes more complicated because you have to take into account factorization properties. So in other words, you don't just need to consider the correct or the proper elicity weight, but also you have to consider the fact that this amplitude needs to have poles in prescribed position, and that those poles need to correspond to physical internal momenta going on shell. You can see, just say that you try to attempt this expression, say that you attempt guessing this amplitude from first principles. It's not as easy as the 3.1, right? So here you can appreciate that you have the right elicity weight for everything, and that you have sort of some poles in the right position. What does it mean to have some poles in the right position? Means that, well, look at an intermediate representation of the amplitude in here, in which poles are more manifest. This can also be rewritten, if you like, at S14, right? So you know that these poles corresponds to either the sum of momenta 1 and 2 or the momenta 1 and 4 going on shell. It's not immediately as clear in here, but probably you would have to work your form back and you figure out that these are poles which are allowed. However, if you want to do amplitude at higher points, there are better techniques, namely recursive techniques, to obtain without having to do so much guessing. They still correspond to the bootstrapping philosophy, but require usage of information at lower multiplicity. And this will be the topic of the lecture tomorrow. I would not want to start a new chapter in case just with 5 minutes left, so I hope that there is some question here. Yes. Mm-hmm. What extra matter field are you thinking about? Yes. Mm-hmm. Yeah. Sure. Yeah, that intuition is very correct, but let me rephrase your intuition in a different way, which is quite more interesting to me. So the theories are like the most supersymmetric theories, right? But say that you are supposed to get an amplitude for gluons in QCD. Forget about that's going to be the same as n equal to 4, right? If you just put external states, which are the gluons, or if you wish, no matter once at loop, you're going to have problems or differences, right? And problems, but at 3 level, you can reuse that result. And actually, a lot of the selling point of having results at 3 level for supersymmetric theories, like, look, that's a subsector of this is going to be QCD or, say, SUN generalizations thereof. At loop level, a lot of technology, in the early, or say the I don't know, early ages of amplitudes. But at loop level, people were still using supersymmetric results, but then subtracting. So like writing n equal to 4 going into the loop, and then taking away some scalars and take away some fermions. And this would be an organization in a sense, but an organization which actually simplifies the calculation. Yeah. Other questions? Okay. So I would say then that we close today with 3 minutes ahead of schedule. Yes. Thank you.